So a perceptron can learn anything it can represent. So anything that can be separable by a linear solution is something that can be done by a simple perceptron. Now, what's the hyperplane? If you consider a plane, two-dimensional plane, this plane can be perfectly split into two parts using line. Line is a one-dimensional aspect. If I give you one line, this line can be split into two parts using one point. So one point or one-dimensional solution can split this into two parts. A two-dimensional can be split into two parts using one dimension. So similarly, what if you had a three-dimensional structure? Imagine the room that you are sitting in. It has length and width and height as well. So it has three dimensions. So in order to completely split it into two, you will have to use a plane. Okay? Up literally, you build a wall between the first and the second part. It would be again a two-dimensional structure. So in order to split the three-dimensional, what you need is two-dimensional structure. Over here we've got X and Y and Z. So anything beyond, what happens to things that are beyond three dimensions? In order to split something that was in four dimensions, you'll require a three-dimensional solution, and so on and so forth. The higher up the ladder you go, one lesser solution is what you require. So up until three dimensions, we've got a plane. Anything beyond that, we've got a hyperplane. Hyperplanes or hyperdimensions are those we cannot visualize. Okay, so anything separable by a hyperplane, line, point is something that our perceptron can represent. Now consider this example. If you can look at these data, what do you see? Value of x1 and x2, these are the input features, and value of y. If both of these are 0, then value of y is 0. Input features, if any of the input features is 1, then the output is 1. And if any of both of the input features are 1, then the output is 1 as well. So this is basically an OR function. And let me remove some of the content over here so we can easier see. So what the OR function does is takes both of these inputs and splits these. So it's taken the feature space and split this into two parts based on the inputs we receive. So here is a formal expression of it, or a formal definition. So we've got some weights, and based on those weights we use the values of x1 and these weights in order to determine this output. This is an exercise I'd like you to do at home as well. Okay? Please remember that you have to implement the OR function using different weights. Which weights? These are given over here, but there are some others that you should experiment with yourselves. So the inputs remain the same. We've got 0011 and 0101, while the weights can be different. So for numerous set of weights, you can come up with an equation that would split your feature space. So if the equation was over here, instead of -3, this was -2, it would have still worked. So instead of again -2, it was -1. Now this is a running of the same example. We've calculated the weighted sum of the inputs, and based on that, we've found the outputs. Again, I'd like you to do this exercise by pen and paper and try using different weights. Here is another function that we can use. A perceptron can be used for many Boolean functions, because again, Boolean functions produce output in two dimensions. Either it is a plus class or a minus class. So that's something a perceptron can easily do. Here is the AND example. So in case both outputs are 0 or inputs are 0 or the inputs are different, then the output is negative. And if both inputs are 1, then the output is positive. So we've set some value of W0, we've set some value of W1 and W2, and based on that, we produce some output or results. Here is the complete calculation. We plug in the x1 and x2, we plug in the values of the weights, and this is the value of the activation function. And based on the value of the activation function, these are the outputs that are produced. So mathematically, this is what it would look like. The feature space is again divided into two parts based on the single equation or single line. Here is another function, XOR function. Now, do you think that you can represent an XOR with a perceptron? How do I determine that? First, see what the trend of the pattern is. For 0, 0, I have -1. For 0, 1, I have +1, 1, 0, +1, 1, 1, -1. What does that mean? For similar inputs, we have negative. For different inputs, we have positive. Now, the feature space is not split into two parts, it's rather split into sections. So if we have different inputs, then we've got a positive solution. And if we have similar inputs, then we have a negative solution. So in this case, we have to split our feature space into two portions. And this two portions is something that cannot be done by a single perceptron. For this, we need something more sophisticated. So we can model the AND operations, we can model the OR operations, primarily because of the reason that one line or one split is enough to break the feature space into two portions, but we cannot do the XOR operation. Summarizing all of this, the aim of a perceptron is to classify inputs. Inputs can have any number of sizes, but into only two classes. So classes can be binary, either first class or the second class. So one single perceptron divides our space into, using a hyperplane, into two parts, two decision regions, and the equation for that is given as such. We've got weighted inputs and we've got some threshold value. If we exceed the threshold value, then we get the output equals to 1, and if we are below the threshold value, then we get the output equals to 0. So a two-input perceptron, or something that is two-dimensional, would split into one region or one line. If we've got three-input perceptron that has 3 dimensions, then it would use a plane for separation. Okay? Next up, we have the perceptron learning. This is something we do later.